Now we're going to look at optimization problems. Now this is one of the most enjoyable parts of doing calculus with the derivative. This is where we get to actually solve some practical problems. And I think you'll enjoy them too. First of all, let's talk about what optimization actually means. What it means is looking at maximum and minimum problems as we have been doing. Now the word optimization is used in many of these situations because optimize or optimization means to find the best. And that's what we want to do. We want to find the best in these problems, the best solution. And sometimes that means a maximum, sometimes that means a minimum. Now in order to attack these efficiently, let's go ahead and adopt a strategy. And what I would do if I were you is, I'm going to list a series of 5 bullet points here. And it doesn't have to be 5, it could be 4 or 5 or 6. But you write down a series of bullet points that give you guidance as to a procedure. And this is the sort of rough way that you want to attack problems. The first thing you need to do, and this is something students are sometimes reluctant to do, but draw a sketch. Most problems benefit highly from having a picture to clarify what the notions are. The second thing is you want to label relevant quantities. At the same time you're drawing a sketch, label the relevant quantities. And those are going to be the things you're looking to maximize or minimize. Secondly, once you know what those quantities are, find by some means a formula for the one quantity. I'll even make a note here that it's the one quantity. The one quantity to be optimized, or to be more specific, maximized or minimized. And this is important so that you know mathematically what it is you're looking for. And you can only look for one single quantity because the calculus we're doing is single variable calculus. And that will come up next. Use given information, so this is information that comes from the very nature of the problem or from your own past experience in mathematics. Use the given information to write that formula that you just found, which may have more than one variable, as a function of just one variable, because that's the only kind of calculus we are doing at the moment. Then before you go any further, this one variable represents something in a practical problem, so it's very important to understand what its limitations are. In other words, find the domain of that variable. And that will be the domain in this problem as restricted by whatever restrictions are given to you in the problem. Then finally, we get to the point where we get to pull in the calculus. We will use the derivative, what we've been studying all along here, to find the desired, and we'll be looking for global maximums and minimums. What is the highest and the lowest point on the curve, which is the graph of the function of one variable here. This is what we are going to do. So once again, write this down yourself, keep it near you as you work on problems, and it will help guide you through this process as we work through the actual details of individual problems. Now we'll start looking at some actual problems. And the first kind are problems in which the domain of the variable is a closed interval. Now you know from our past experience that if you're on a closed interval, you're guaranteed, if the function's continuous, to have both a global maximum and a global minimum. And we'll look here at maximizing area or volume and minimizing cost. So the first problem we'll look at is really a classic, and I'll just call this the box problem. And here is how it works. Imagine you have a sheet of cardboard, a rectangular sheet of cardboard, something like this. Now, what we'd like to do is cut out a corner from each one of exactly the same size. Let's see if I can draw these exactly the same. And then, with these corners removed, so you can imagine that they have been pulled away, then in here we could fold up the sides. So we'd fold up these 4 sides to create a box with an open top. So these corners now are going to be totally removed. And we then fold up these sides to form a box. Now let's give some dimensions to this. Let's make this sheet of 30 inches in this long direction. And let's make it 16 inches in this direction. And the squares that we have removed from each one of the corners is exactly the same, so they all have dimensions x by x. Okay, so that's what we want to do. And then the question we want to ask here is, what value of x, because x can have various values, it can be a very small square or a very large square, what value of x yields a box of largest volume? So clearly what we need to do here is maximize the volume of the box that is created after we take these sides and we bend them upwards along these dotted lines. Now before we go to the next page, let's observe one other thing, that we can see the lengths of these seams by just seeing what we have here. The total length of the sheet is 30 inches, and we've removed x and x on each end, which means this distance in here has to be 30 minus 2x. Likewise, vertically, we have the 16-inch dimension, and then we've removed x and x, so this dimension is going to be 16 minus 2x also. So we'll use that on our calculation of the volume here on the next page. But keep this picture in mind. Okay, in this solution, we are looking to maximize the volume. So let's write down a formula for the volume. The volume is the height times the width times the depth of this particular box. Now we have the dimensions from the previous page. It's going to be x high when we fold up those sides, and then the other two dimensions are 16 minus 2x and 30 minus 2x. So there's an expression for the volume, and we're lucky in this problem, it's automatically in one variable, which is very handy. Now, we can do a little algebra here, multiply this out. The reason I'm doing that is it will be easier to find the derivative if this is multiplied out. It is nice to have the factored form for some purposes, but for the derivative, it's helpful to have it multiplied out. So I can replace volume by v of x, because it's all in one variable, and if I multiply this out, I get 480x minus 92x squared plus 4x cubed. And this is just a little bit of algebra I'm leaving to you. And this will be defined where x is in the interval what? Let's see. Well, the smallest box we could choose to cut out of the picture is the side 0. That would be cutting no box out of it. Now, of course, you wouldn't get no little square out of each one of the corners. If we take 0, of course, then we haven't really made a box because we've got nothing to fold up. But at least mathematically we want to include that. And then how big could x be? Well, let's see here. Let's take the picture back and ask ourselves, the same little x box, little x square is being pulled out of each corner. What is the largest x could be? Well, it's going to be limited by the length of the two sides. In fact, if you notice, this box that we're cutting out here, this square, can't go any farther than the middle point here. You could take an x as far as being 8 inches long, but no farther, because this one would have to come out also and be 8 inches. So that means x cannot be any bigger than 8. So x would be in the closed interval from 0 to 8. And this will be our function, representing volume here, and the domain of the variable, which is very important for us. And I've already mentioned how we got the 8 as half the shorter side. Now let's go ahead and start using the calculus. We need the first derivative in order to check where critical points are, so we can look where global maxes and mins are. We already know what the endpoints of the interval are. We'll check those later. So the first derivative is going to be 480, just looking here, minus 184x plus 12x squared. Again, by a little algebra, since I now want to set the derivative equal to 0, I want to factor this. A little algebra leads you to 4 times x minus 12 times 3x minus 10. So I'll let you check that out. And then, first of all, I'll put this in parentheses, but it's worth mentioning. Remember, critical points are where the first derivative is 0 or where the first derivative doesn't exist. Students tend to forget that you need to check that it does exist. Now, in this case, this derivative does exist because the derivative is a polynomial which exists and is defined everywhere. So I'll just put that in parentheses as a reminder. Now, what we're really interested in here is where this first derivative is 0, and that'll be 0 for, let's see, x equal 12, or from this one it would be 10/3. Now remember our domain for x, 0 to 8? That tells me immediately that this is out because it's outside the domain. So I don't have to consider the x equal 12 case. It makes no sense in this problem. So there's only one candidate, and this is a critical point. It happens to be a stationary point, to be specific, but it is a critical point. Now, to look for a global minimum or maximum, in this case I'm looking for a maximum, what I need to do is check the original function at the two endpoints and at any critical points that have turned up. So I will now check v at 0, which is one endpoint, v, the original function again, at 8, which is the other endpoint, and then finally v at 10/3, which is our one and only critical point. Now if you think about it, if the box or the square that you're cutting out at each corner is of size 0, and here's the picture, we can talk about it from the picture, then you've cut nothing out, which means there's nothing to fold up, and so the volume of the box, which really isn't a box, is 0. On the other hand, if the box that you cut out is actually this large, it's actually 8 by 8 in each of these corners, then if you try to fold this up into a box, you see that you're going to just get a fold along here, and again, you won't have any volume. So it's clear from practical considerations that the volume in both of these cases is going to be 0. The volume in the case that you have 10/3, your critical point, turns out to be approximately 726 inches cubed. And you can do the arithmetic to check that. You just put the 10/3 in the original function here. So it looks like this is going to be our global maximum because these two are certainly lower. So this looks like this is our global maximum. And it is occurring here when x is equal to 10/3. And that is all we need. And that's 10/3 in inches. Now you can do some other checks here if you want. You can try the first and second derivative test, but remember, they check for local maximums and minimums. And in this problem, we're interested in globals, so although that will verify what we've done, it's not necessary. Finally, as one more step, which you should always do in a problem, look at the graph of the function to either get a hint as to what the maximum might be or to verify that your work is correct. This also gives you a visualization of the problem that is unlike what we've already seen. So if you graph this v of x function, you get something that looks like this. So this is v of x, which is the volume function. The global max, of course, occurs right here, visually obvious, and that's at 10/3 down here. The domain was from 0 to 8. This axis is in inches. This axis is in inches cubed because it's volume. And this height here, this is approximately 726, as we found out. So there you go. There's one example of an optimization problem. And we've got all the pieces. We've drawn the picture, found the formula, found it in terms of a single variable. Let's now look at a second problem here, which involves another kind of situation. This is a situation in which we have an oil well offshore somewhere. And let me mark the shore here like this. Mathematical shore, always a straight line. And the oil well is known to be, say, 5 kilometers offshore. So that's what this dotted line represents. And I'll mark the point here where we are measuring from to be A. Now what we want to do is we want to deliver the oil to a point here B. There are two ways to go about it. The oil well is offshore here, so this is water out here and this is land down here. The oil can go in a single pipe from the oil well directly to the point B, totally underwater, or it can come down here directly to A, or to any point along here, that part being underwater and then the rest under land or on land. So the question is, what is the most efficient way of doing that? What is the most cost-efficient way of doing that? So let's draw a picture and say, I don't know where it's going to strike here. It could be A, could be B, it could be somewhere in between. When you have that option, always draw an in-between picture. So let's just suppose that it's going to strike here at some point P. So the oil pipe would come down here to P and then go over here to B. And this, of course, is the shore, and this is the land side. And let's suppose that A and B are known to be 8 kilometers apart. And so where it strikes at the shore here is some unknown distance from A. Let's call it x for the unknown distance, and then the remaining distance, of course, would be 8 minus x. So what we want to do, just to write this down, we want to pipe the oil to B, and we want the pipe to meet the shore at some point P between A and B. Now, of course, it could be A. That may be the most cost-efficient way to do this, or it could be B, but it's more likely in most cases to be somewhere in between. So now you need one more piece of information before we can pose the question. You have to know how much it costs to put a pipe underwater or to put a pipe on land. And as you might expect, it's more expensive underwater. 1 kilometer of pipe underwater costs $1 million. Whereas 1 kilometer of pipe on land will cost only half that much, $500,000. So what we want to do here, as a practical maximization problem, or minimization problem in this case, locate the point P in order to minimize the total cost of running this pipeline. And of course, locate P in this case means, since P is here at a distance x away from A, means to find x. So that's the language we'll put it in for ourselves. So there is the problem we are going to try to solve. We want to find the most cost-efficient way to do this. And this is very, very practical. Many, many problems in business in particular are all about finding the best way to do something that is most cost-efficient. And this is just an example of that. So, in order to work this out, let us start by, first of all, letting some letter, say C, stand for the total cost. And let's find out what the calculation of the total cost would be. So this will be the total cost, and we'll measure this in millions of dollars. That way we'll keep our numbers small. So when I have 1 in the cost, it'll be 1 million, and we'll put the millions on later. Now, we want to find out somehow how much this costs. Well, if you look back at the picture, it is going to depend on the length of time you're underwater and the length of time you're on land. The time on land is 8 minus x. That's easy. The time on water is this distance, which we'll have to compute from this right triangle. So let me redraw the right triangle here so we have it in front of us to work on. This is the point P down here. This point up here represents the oil well. This is right triangle. This distance is the x, and this is 5 kilometers from shore. So we now know that, using the Pythagorean theorem, that the distance from the oil well to the point P is going to be equal to, Pythagorean theorem here gives us the square root of x squared plus 5 squared. That's 25. And again, this is the Pythagorean theorem. So this is one of the kinds of things that you might have to retrieve from your memory when you're doing problems like this. See, this was never mentioned in the problem. It's something you have to think of based on your experience. So, with this piece of information, knowing the distance of the pipe will be traveling underwater, I can put down a cost equation. So the cost, which is now a function of x, will be 1, representing $1 million, times the length of the pipe underwater, plus 1/2 million, that's the 500,000, times the length of the pipe on land. And this is where x is in, let's see, x here could be 0. That's if the pipe goes directly down to this point. I think we called it A. And x could be as much as the entire distance between A and B, which was 8. So here is our cost function on this interval for the variable. All right. Now we're going to look at the derivative, as we always do, to find critical points. To check for global maximums and minimums, we check endpoints and critical points. So the first derivative here will be the derivative of this function. And I'll think of this as x squared plus 25 to the 1/2 power. So I'll bring the 1/2 power down, x squared plus 25 to the minus 1/2 power times 2x, plus 1/2 times the derivative of the inside here, which is minus 1. Now with a little bit of algebra here, very little, you can rewrite this as x squared plus 25 to the 1/2 on the bottom, x over that, minus 1/2. And I'll just note parenthetically again that c prime always exists. So we only have to look at where c prime is 0. And it always exists because if I look at this fraction, which is the only place it might fail to exist, I notice that the bottom here is always a positive number. And so this will never be 0 and never cause us any difficulty. But now we want to look at where the first derivative is 0. So let's check that out next. C prime will be 0 for when x over x squared plus 25 to the 1/2 equals 1/2. Well, we cross multiply here. We get 2x is equal to x squared plus 25 to the 1/2. Then we square both sides. And you have to always be careful when you do this operation because you may be adding solutions that are not part of the original problem. We'll see if that happens. We get 4x squared here. This square gets rid of the square root, which was the whole point. X squared plus 25. That leaves me with 3x squared is equal to 25. So x is going to be equal to plus 5 over the square root of 3 or minus 5 over the square root of 3. But it can't be minus 5 over the square root of 3 because x is a positive distance, or at worst, 0. So this can't happen, not in the domain of x. So this is our only critical point, the point where x is equal to plus 5 over the square root of 3. So again, to check out where there are global maximums and minimums, we take the original function evaluated at the two endpoints, which were 0 and 8, and then also evaluated at this one critical point, 5 over square root of 3. Well, let's see. If we put 0 in the original function, we get 5 plus 1/2 times 8, which is 9. If we put 8 in, we get the square root of 89, which is approximately 9.4. And we need to have some sort of approximation here because I need to compare these to find the largest. And then when I compute this one, if I simplify it, I get approximately 8.3. And if I want to be more specific, and you'll see why in just a second, this would be approximately 8.330127. Now in this problem, we're looking for not a maximum, which would make this 9.4 the global maximum, but 8.3, which is the global minimum. That's what we're really interested in, because we're minimizing cost after all. So with that in mind, I can now write down the minimum total cost. I know where it occurs now. It occurs when the x value, the position that I will be bringing the pipe to shore, is 5 over square root of 3 units, in this case kilometers, from the point A. But the minimum total cost then will be this number multiplied by 1,000,000, because remember the cost was in units of 1,000,000. That's why I have these extra decimals here. So I can write down 8,330,127. And this will happen when x is equal to 5 over the square root of 3, which, since you're going to have to measure it, is approximately 2.89 kilometers. And there you have it. That's what we needed to solve this problem. We know exactly where to bring the pipe to shore so that the minimum total cost, well, that the total cost is a minimum, and that minimum will be this much. Once again, always draw yourself a picture of the function, either to enlighten yourself or to verify what you've done. In this one, it's a very subtle picture. It's a subtle picture that goes like that. This is c of x, which here represented cost. The global minimum occurs somewhere over here at 5 over square root of 3. So there's our global minimum. Remember, at this endpoint it was 9. The dimensions, or the units, on this axis were millions. And on this axis, they were kilometers. And you can see the picture here showing that the global minimum actually seems to be in the right place. So we apparently have done the calculations correctly, and we want to see now that we have a visualization of our problem about cost. The problems we just saw were where the domain of the variable was a closed interval, so we were guaranteed of a global max and a min. Now we're going to look at the situation where we don't have a closed interval. We might have an open interval or partially open interval. We'll talk about minimizing materials or distance, mainly materials in this case. And let's do it again by an example. This is another classic. I'll just call it the can problem. And here is the situation. We have a cylindrical can. And it is closed. That means it has a top and a bottom. So a closed cylindrical can. How much does this hold? Well, it holds 1 liter, which translates to 1,000 centimeters cubed. Now what we want to do here is find the dimensions, which in this case are the radius and the height. And the height and radius will be measured both in centimeters in order to minimize the material used to make this can. Now this is a mathematical can. We won't worry about waste and we won't worry about what it takes to make the seams. But the material would be the top, the bottom, and then the part that goes around. We want to minimize that material. So that's our job here. So we already have a picture, but we need to do a little more with the picture. It's not enough to sketch a picture. As we said in our strategy, we want to also label appropriate parts. Now since radius and height turn up, let's go ahead and label them. Here's the radius of the can, and then this would be h, say, for the height. So r for the radius, h for the height. Let's see what information we are given. We are given the fact that the volume of the can is 1 liter, or since we're doing centimeters for the distances, let's use centimeter cubed for the volume. The volume is given to be 1,000 centimeters cubed. Now the volume of a cylinder is the cross-sectional area at the top, which is a circle, so that's pi r squared, times the height of the cylinder. So that's pi r squared times the height h equals 1,000. Now I'm going to solve here for h only because h is the only variable that is simple. R is squared here, and if I were to solve for r, I'd get a square root. Some point down the line, I will probably have to use one of the two variables. Let's hope that it's h that we'll be able to substitute for. So 1,000 over pi r squared. So this is the kind of thing that will be useful later, and very often when you're doing these problems, you don't think to do this immediately. You don't think to do this till after you need it. But we'll do it now because we see it. One more thing. This says minimize the material. Now we're not going to worry about the thickness of the material. So what does that actually mean in this case? Minimize material means to us, mathematically, to minimize the surface area. And we'll go ahead and call this S. So the surface area would be the top, the bottom, and the part going around. All together, that will have an area, and we refer to that as the surface area of the cylinder. That's what we want to minimize here. That's what minimize the material means. So surface area is what we're interested in. That's what we're calling S. And we need to come up with a formula for the surface area. Well, first let's draw a picture so we see what we're doing. We have a top. We have a bottom. Both of these are circles. And we have the part that goes around. So maybe I could draw it like this, just to give you the sense that we're talking about the part that goes around. That part has a height of h, and what is the distance around? Well, that is the circumference of one of these circles. So that's 2 pi r. So that means I could write S here as these two areas added. That'd be 2 times pi r squared, plus the area of this rectangle, which is 2 pi r times h. But there are too many variables here. We are doing one variable calculus. So I can't take the derivative of something with two variables as it stands. So I need to get one variable. Well, recall what we did on the other page, that we wrote h as 1,000 over pi r squared. That puts h in terms of r, so we can put this entire expression in terms of r. In other words, we can write this as the function s of r. So that's 2 pi r squared plus 2 pi r, and now replace the h, by 1,000 over pi r squared. And then if we simplify this a bit, we can write s of r is equal to 2 pi r squared plus 2,000 over r. Because one of the r's cancels, the pi cancels, and the 2 multiplies to give you 2,000. And this will be true where r, the variable r, is in what interval? Well, let's see here. We cannot, practically speaking, have r equals 0 because then there would be no circle here and hence no cylinder. More importantly, in the actual expression here for surface area, notice that r is in the denominator, which means r can't be 0 because we don't divide by 0. So r must be positive. R is a distance after all, and not equal to 0. And how far up can it go? Well, in fact, there are no restrictions here. R can be as large as you want. Now, the cylinder you get, if r is very large, is not going to be very high, but it still will be a legitimate cylinder. So that is to say, r could come anywhere from 0 to infinity, the open interval. This is an open interval, unlike our other problems, and there's no upper limit. So here's the situation we have now. We have the surface area written as a formula, and we know the domain of the variable. Now we continue as we always have. In order to look for a global maximum or minimum, we go ahead and find the first derivative. The first derivative, just looking here, is going to be 4 pi r minus 2,000 over r squared. You could rewrite this as 2,000 times r to the minus 1 and then take the derivative, and that's what you would get. This can be simplified into a single fraction, often a good idea, especially if you're going to set this equal to 0. R squared on the bottom, so this would be 4 pi r cubed minus 2,000. Now I'll put parenthetically again that s prime exists. This expression exists. Why? The only place it wouldn't exist is where r would be 0, but we eliminated that from the domain. So this expression will always make sense. That's worth noting. Now we're really interested in where this is equal to 0. Well, the only way a fraction can be 0 is if the top is 0. So this will be 0 for 4 pi r cubed equals 2,000. If you then solve this for r, a little algebra, you will get 500 over pi and the cube root of that. And that, just for a record on the next page, is about 5.4. This is a critical point. In fact, a stationary point. So this is a critical point. This, realize, is an open interval, so there are no endpoints here to check. So this is the only point that is likely to give us our answer, which would minimize the material. We'll have to see if that's actually the case. So to see that our r value, which is 500 over pi cube root, that this actually gives a global minimum as we desire it to, either, you can do one of two things here. Either note that if you take the limit of the original function s as r goes to either one of the endpoints of the interval where the r is defined, if r goes from 0 to 0 from above, or as r goes to infinity, in either case the surface area blows up to infinity. So it's not going to be giving us any kind of value at the end, so it means that whatever minimum, whatever value we get for this value of r is going to be certainly less than infinity. So you can either do that, or you can observe the following, that if you take the second derivative, which is the second derivative of s, which is 4 pi plus 3 times 2,000 over r cubed, that is always positive because the r value is always positive. So this expression is always positive, and that means that we would get a local minimum, because if the second derivative is positive, it's concave up. So there'd be a local minimum happening at this point. Well, if it's a local minimum, it's going to be a global minimum as the only choice here. Finally, again, we'll look at a picture to verify a little bit more strongly what we've done. The actual graph of this function looks something like this. There's a global minimum here, the one we calculated, which occurs at 500 over pi cube root. This distance is measured in centimeters. This is the surface area function, S of r. So surface area. And the height up here, well, let's see, this will be centimeters cubed. I don't really need to mark the height, but if you want to graph this on a calculator, maybe go up to 2,500. That might be a way to see this. And here is your picture. And you can see the global minimums right here, and the graph of the function looks like this. It certainly seems to be going up to infinity in both directions, as our limit proved. So there is the second of two examples to show you how you can deal with a situation where the r value here is coming, let's write this out, where r is in an open interval, like this one. Now, for those of you interested in economics, here's an economics application. We'll talk about things like revenue and profit, cost, and marginal analysis a little bit. An economics application, okay. During some time period, let's give some definitions here. During some time period, let's let C of x be the total cost, so C for cost, of producing x units of whatever the product is we're interested in. Let's let R of x be the total revenue, so R for revenue, from selling. This is the money you bring in from selling x units. And finally, P of x will be the total profit from selling these x units. Okay, so there are some basic definitions. So profit is defined to be what remains after you take your revenue and you subtract away the cost. So that's P of x is defined to be R of x minus C of x. Okay, good. Now, further, what else can we say based on some knowledge from economics? We can say that cost, C of x, can often be written as a fixed overhead, plus M of x, say, which is a manufacturing cost. So this would be a fixed overhead, and this would be something you'd have to pay regardless of whether you produced even one unit, whereas the manufacturing cost, that depends on how many units. So this will depend for X units on how many units you have there. So that is the cost. Also, in economics, although we won't do it here, it can be shown, and if you use appropriate assumptions, it can be shown that the M of x here, the manufacturing cost, can be written very often as something like bx plus cx squared. That's a quadratic without a constant term. So putting these things together, we can write the cost as A, the overhead, plus the manufacturing, which is bx plus cx squared. So here's a new way to write the cost. Also, if you know the price of each item, if each item is sold at a price of P dollars, then that means we can write the revenue as P dollars per unit. So it's P dollars times the number of units. So with this revenue written this way specifically and the cost written specifically this way, we can write a formula for the profit. Profit, P of x, can be written as the revenue, of course, which is Px, minus the cost, which is A plus Bx plus Cx squared. Now that is the formula we can use for the profit. Now we'll have to come up with the actual numbers A, B, C, and P depending on circumstances. Let's do an example here. Suppose you have liquid penicillin, and that is being sold at $200 per unit, whatever the unit size is. Let us suppose that we are also told that the cost is computed as 500,000 plus 80x plus 0.003 times x squared, where x is the number of units sold. Another piece of information is that production capacity in a given time period, whatever that time period may be, is at most 30,000 units. And finally, we can ask our question. How many units must be manufactured and sold in order to maximize profits? Now, this is a very common kind of calculation that people in business are interested in computing. Now, we have a formula for profit up here, and we're given some information here. We're giving a cost function, which is this part here, remember, and we're told the cost per unit, that's the little p. So we can calculate profit using this formula, and then we can maximize that profit. So let's go ahead and see how that works out. Profit, which here is in dollars, can be written, as I just said, as P of x equals little p times x, which is $200 per unit, minus that cost function, which is 500,000 plus 80x plus 0.003 x squared, where x, which is the number of units, comes from the interval, let's see, there could be 0 units, you don't produce any perhaps, up to 30,000, which is the capacity of the production. So that is our profit function for this particular problem. And we would like to maximize this profit. So what do? We do exactly what we've done in every other case. We look for critical points. We already have the two endpoints to check, and the critical points come from looking at the derivative. So this is 200 minus 80 minus 0.006x. And by the way, when you look at derivatives of these economics functions, that's what is usually referred to as talking about marginal analysis. And you can try that on your own and read about it in economics books. Now, p prime here always exists because this is just a polynomial, in fact, just a linear function. So we're interested in where p prime is 0, and that will be 0 for where this expression equals 0, which is when 0.006x equals, and put this on the other side, that would be 120. Solve that for x, you get 20,000. And this is, in this case, our one and only critical point. So just as before, we go back to the original function and calculate it at the two endpoints in the critical point and find out which one gives us the biggest number. So we'll calculate p of 0, p at 30,000, and then p at 20,000. Now, you can do these calculations yourself, so I'll just write down the results. If you put 0 in there, you get minus 500,000. Not the kind of profit you'd like to have. That probably means you need to pay somebody 500,000. If you put in 30,000, you get $400,000 of profit. But if you put in 20,000, it turns out you get $700,000 of profit. This certainly is a global maximum. And this global maximum occurs at x equal 20,000 units. So now we know that it is better in this case to produce 20,000 units rather than the maximum capacity of 30,000 if you want to maximize your profits. Here is the picture, as I always recommend you draw, to emphasize what we just did. The curve looks something like this when you graph it. Here, of course, is your global max. And that is occurring down here at 20,000 units. So this is in number of units On this axis, the maximum here was 30,000 units. 0 was the lowest. If you compute the profit at 0, you get 500,000 negative, because remember this is P of x, the profit function. And the maximum here was $700,000. And this axis, of course, is in dollars. So this just shows us that what we did before is in fact correct. This picture represents visually what was meant by saying the profit has a global maximum or is maximized when you have 20,000 units being produced. Now it's your turn. Let's do some exercises. First exercise is a geometric one. Here is the situation. A rectangle is inscribed in a right triangle as shown in this picture. So I have here a right triangle, and we were going to inscribe a rectangle in this form so that a corner of it here is in the right angle corner, and one corner up here touches on the hypotenuse. Now let's suppose that this triangle is 8 in this direction, 6 in this direction, and 10 along its hypotenuse. Here is the question. Find the dimensions of the rectangle here with greatest area. Now you see the rectangle could be as low as down here, or it could be very, very high and thin here. There's a whole variety, an infinite number of such rectangles in this form. The question is, which one of these many has the greatest area? Now it's time for you to give that a... Let's see. We have the right triangle here. And the right triangle, let's see if I remember, has dimensions 8 in this direction and dimensions 6 in this direction, and it's 10 along the hypotenuse. Now I'm needing to talk about the area of the rectangle, so I'm going to give the length of its sides names. So let's call the one on the bottom, say, x, and the one on the side, say, y. X horizontal, y vertical, seems natural. That then makes this top part here 8 minus y, and it makes this bottom piece down here, let's see, 6 minus x. Now the area of the rectangle that I'm interested in is equal to height times width, which is x times y. And again, I see I have too many variables. I have one too many in this case. So I need to find a way to relate the x and the y so that I can remove one of them and write the other in terms of the first one. Well, it turns out the relationship is going to be something from this triangle. And in this case, the thing that you might want to notice is that you have a couple of similar triangles floating here. This is something else you want to remember from your past experience with geometry, similar triangles. This is something that turns out to be very useful in many circumstances. So if I just draw the triangles, I might have them something like this here. Just drawing triangles like those. What are their dimensions? They're both right triangles, of course. This is 8 minus y. This dimension here is x. This one is y. And this one down here is 6 minus x. Now, by the properties of similar triangles, ratios of corresponding sides are going to be equal. So if I take 8 minus y over x, that's going to be the same ratio as y over 6 minus x. That's what it means to be similar triangles. So from here I see that y and x are related, and I just need to solve for one in terms of the other. It doesn't matter which one you choose. If you cross the multiplication here, you have 8 minus y times 6 minus x equals xy. If you multiply everything out and do a little bit of algebra, if we solve for y, say, you'll get y is equal to 8 minus 4/3 x. So now I have y in terms of x, which means in my area function I can make this totally a function of x. And that's what I'm going to do next. Thus, the area function is now a of x, and that's going to be x times y, and y was 8 minus 4/3 x from the previous page. And I'm going to multiply that out for simplicity, 8x minus 4/3 x squared. And this, remember, is where x is in, well, let's see. X can't be less than 0, although it could be 0, because it's one of the dimensions of the rectangle. And how big could x be? Well, remember where x came from in this previous picture. X is the rectangle's base. The triangle only has 6 units in it, so the x can't be any bigger than 6. Could be 6, though, in which case at either end, of course, we don't have much of a rectangle. Okay, so now we have our function and the domain of the variable, which happens to be a closed interval in this case, which is good. We are guaranteed to have a global max and min. So we'll go ahead and check now for critical points to add to our two endpoints. So the derivative here, looking here, is going to be 8 minus 8/3 x, which is 8 times 1 minus x over 3. This will be 0. This first derivative will be 0 for, let's see, if x is 3. That will make that 0. So that is a critical point, the only critical point here, and it's a stationary point. Now to check for global maxima or minima, we're looking for maxima here, or maximum. We check the original function at the two endpoints, 0 and 6, and also at any critical points we found, which was 3 in this case. If you put 0, and here's a of x, if you put 0 in, you get 0. You put 6 in, you will also get 0. And that makes sense because you don't have a rectangle, physically speaking, if you have x equals 0 or 6. Finally, we have 3. If you put 3 in here, you get 3 times, or 3 in the first derivative rather, 3 times, let's see, oh no, we're putting it in the original function, 3 times 8 minus 4/3 times 3, that will give us 12, which is a global max because it's bigger than either of the zeros. So we now can answer the questions that we were asked to answer. What are the dimensions? Well, we know one, x is equal to 3. That was given right here. When x is equal to 3, we get this value. What is y? Y is equal to, you may remember, 8 minus 4/3 x. That was the y from before. If x is 3, that means 8 minus 4, so y is equal to 4. There are the dimensions of the rectangle. And just to check, as I always like to do, the graph, on the interval from 0 to 6, we get a graph that looks something like this. It's an upside-down parabola. It has its global maximum there at 3. This is a of x, our area function. And the height here is 12, as we just discovered. So now we can see what's going on here in this problem, and I hope that's what you got while you worked it out. Here is another one to challenge you. Another classic, actually. Suppose you have a piece of wire, and the piece of wire is of length 12 inches, say. Now, what we will do with this wire is it will be bent into a circle, or it'll be bent into a square, or it will be cut into two pieces to bend into both a circle and a square. The question then is, how much wire should be used in the circle, should be used in the circle, keep that in mind now, how much wire should be used in the circle in order to minimize, that is, make as small as possible, the total area of the two figures, or the total area of the figures, I should say, because in the first two cases you're only going to have one figure. So once again, you have a wire of 12 inches, you want to bend it totally into a circle or totally into a square, or cut it in two pieces, bend one piece into a circle and one piece into a square. The question is, how much wire should be used in the circle part to minimize the total area of the figures? That's your challenge. We have our wire, which is 12 inches long, and we want to put a cut in it. Now you might say, well, that's only part of the problem. Well, just wait a second, and let me tell you here. Suppose the cut on this side is x, and the cut on this side will be with whatever is remaining. If this is 12, then the remaining part is 12 minus x. Now, as a student, be careful that you don't use too many variables when you set up problems. Try to keep the variables as few as possible. And in this case, I could write x and y, but y is actually 12 minus x. That saves me a variable. Okay, now I said, why would we want to make this a cut? Isn't that only part of the problem? Well, if the cut is at a distance where x is 0, then the cut is at this endpoint, which means the whole thing is going to be bent into, say, a circle. And if the cut is at the other endpoint, then maybe the whole thing's bent into a square. So those other two cases are really part of the continuum of all the cases. So I only need to solve the problem where there is a cut, and that would answer all the questions. Let us suppose we take this first part, and maybe that's going to be the part that gets bent into a circle. So it'll be bent into a circle. A circle's primary dimension here is r. And the wire is the circumference of the circle, of course. So circumference. And so that means x, the amount I have picked here to make the circle, must be equal to 2 pi r, which is the circumference in terms of this radius. And so I want to put things in terms of x, so let me solve for r here while I'm here. So r is equal to x over 2 pi. Okay. Now let's take this other part, and this will be bent into a square. So this one will be bent into a square, and square has 4 sides that are all the same. We'll call that s. The distance around is the part that we're marking with this wire. So this is the perimeter. Instead of calling it circumference, it's called perimeter here. And that means the wire, which is 12 minus x, must equal the perimeter, which is 4 of these s's. And again, I will solve for s here, so I'll have everything in terms of x. So that would be 3 minus x over 4. Now let me take both of these to the next page. This is just an analysis of the problem as it was stated. We haven't even gotten to the point to address the question. The question is, what is the total area of these two? And then let's see if we can minimize that total area. So write this down. The total area, which I'll use the letter A for, is going to be the area of the circle, which is pi r squared, plus the area of the square, which is s squared. Now we have a formula for r and s in terms of x, which is where the cut is on the wire, so we can put all of this in terms of x. So that means this is a function a of x, which is now pi. R was x over 2 pi, which will square, plus s, which is 3 minus x over 4, which we will also square. And this will be where x is in, well, let's see. X is the cut. The cut can be of 0 length, or the cut can be as much as 12. This is cutting at either of the endpoints. Now, physically, that's not really a cut, but mathematically, it's the extreme situation for a cut, and so we mark it down. All right. What do we do now? Well, we have the 2 endpoints. To find the global minimum or maximum, we look for critical points. That involves taking the derivative. So the derivative here, just running it through here, leave the pi alone, times 2 x over 2 pi to the 1 power, times the derivative of the inside, which is the constant 1 over 2 pi, plus 2 times 3 minus x over 4 to the 1 power, times the derivative of the inside, which is minus 1/4. If you do just a little algebra there, and I'll leave that to you, you will get x times the constant 4 plus pi over 8 pi minus 3/2. So that means that a prime is equal to 0, and of course a prime always exists here. It's just a linear function. A prime is equal to 0 for, you solve this for x. I'll leave the algebra to you. The x is 12 pi then over 4 plus pi. And that is our one and only critical point here. So we have 2 endpoints and a single critical point. And now we want to use these 2 to see if we have a global minimum. So I take the original function and evaluate it at the endpoints, which were 0 and 12. And then the original area function evaluated at the new value we found, which was a critical point, which is 12 pi over 4 plus pi. In the first place, we get 9. That's very easy to check. If you put 12 in for the area, you'll get 36 over pi, which is approximately 11.46. And if you then approximate the value you get by putting in this number, you get about 5.04. That's clearly the global minimum. Now, that is not enough for us to finish the problem. We were asked for the circle, how much of the wire would be used for the circle so that you'd get this global minimum. Well, for the circle, we will have to compute that 2 pi r circumference, which was the piece of wire for the circle. So I need r. So r is x over 2 pi. So this is the x value. So it's 1 over 2 pi times this x value, 12 pi over 4 plus pi, simplifies a little bit to 6 over 4 plus pi. And so I can now answer the question, the amount of wire for the circle, to form the circle if bent, in order to minimize the total area of the two different figures, is equal to 2 pi times r. Here's r. That's 6 over 4 plus pi. And that, I'll put that up here and approximate it here as approximately 5.28 inches. So that answers the question of how much wire would be used. And we can go back up here to the area function, and again, since this is a global minimum, I recommend that you graph the function to see what you've got. So I hope you did this. Here's what I got for a graph. I'm going from 0 here. The graph will look something like this, going out here to 12. Its global minimum is occurring here at the point 12 pi over 4 plus pi, which you can approximate also if you like. It's 9 at 0, and this is in inches squared, and because that was area, and this is in inches. And this is the area function. This is the total area of the two figures created, the circle and the square. And again, it's always nice to see this in a graph so that you have a really strong feeling that what you've done is correct and that this is the right way to go.